So one common problem you might get on an exam, not just in data structures, but pretty much any class where graphs come into play, is given this graph, give me from the starting node, which is going to be A in this case, the shortest different distances. Perform Dijkstra's algorithm on this graph. Okay, so let's just go ahead and just be clear on this. So, right, let's initialize this. It's fairly straightforward to initialize this graph. Okay, A is going to be done, right? And then all the other ones, and hopefully your professors are going to be nice and basically give you stuff that's alphabetical in order. B, C, D, E, F, and G are to do, right? So we've got our set of done and to do, right? Because we're just going to start from A, right? So it's automatically done, don't have to worry about it, right? Okay, and then we list all the other nodes here. We don't have to list down node, I mean, we can list down node A, but, okay, right, it doesn't really go from, it doesn't really have anything, information that's useful for us, so not really going to put it down. So B, C, D, E, F, and G, right? Those are our remaining nodes that we have to figure out. So let's solve for initial distances, right, to initialize the graph. Right, we can get from A to B with a cost of 5. We get there from A. Then we can get from A to G with an initial cost of 2 from A. And then everything else, we're going to put a cost of infinity and do your best to draw an infinity, right? I'm pretty terrible at it, okay? And then put A, and then A, right? Because we can get to all these other nodes from A for a cost of infinity, which is like a lot, so I hear. Okay, so that's the initialization step for Dijkstra's algorithm, and that's super easy to do, okay? And now the rest of it is just so long as you keep your head. This is also very easy to do, okay? So the first thing we need to do is we go through all these nodes, right? We go through all these nodes, and we look for which one has the cheapest distance. 5 is certainly cheaper than infinity, but oh, there's a 2 there. G has a cost of 2. All right, so I'm going to say that, so we found that G has the cheapest cost, and because we iterate through this, find the cheapest cost, we know that of things still to do, that basically figured out that we know the shortest path to G, right? And that works out on the graph too, right? So we know the shortest graph cost to G. So let's see which of G's nodes give us extra information. So we can get to G for a cost of 2, right? So from G to B, that's going to cost us 1. So it costs us a total of, if we go through G, it's going to cost us a total of 3, right? 2 plus 1, or 3 to get to B. That's cheaper than 5. So let's erase 5 and put down 3 and say instead of going from A to G, A to B, we're going to go from G to B, and that's going to have a total cost of 3. Well, how do I get to G? Well, we look at G, and that tells us to get to G, we go through A. See, that's the point of the predecessor. You can kind of trace back how you want to get how to get somewhere. Let's look at this other edge over here. G to E is 3. So that would be 2 plus 3, which last I checked is cheaper than infinity. So we're going to go ahead and first check to see. Yeah, okay, so 5 is still cheaper than infinity. So I'm going to put down 5 here, and I'm going to put down, we can get to E from G. Okay, so the next thing we're going to do is that so we're done here, right? So now we go through our to-do list again and say, okay, which of these has the cheapest cost? B has a cost of 3, which beats infinity, 5, and infinity, so B has the cheapest cost. Let's just go ahead and say, boom, we found the cheapest way to get to B, and look, that's true, right? It is true, 2 to 1. 2, 1, cheapest cost to get to B. Okay, so now let's look at all these other edges, right? These edges that B has given to us, right? So cost of 2, B to C, that's a cost of 2, plus the initial cost to get to B, which is 5. Sorry, not 5, right? But 3. That's why you want to look at the table. So it costs a total of 5 to get to C, which is cheaper than infinity, so we'll go ahead and put that down. about this node? Well, it's 3 plus 3 to get to f. Right? So 3 plus 3 is 6. Whoops. 6 from b. Right? So we figured out, right? 3 plus 3. Right? We don't do 5 because that's not the cheapest way to go. We're going to go through, to get to b, we want to go through g, which is a cost of 3. This is 3. Yes, to get to b from g has a cost of 3, right? Because this over here is the cost to get to g, right? To get to b, it was 1 more, right? So 3 plus 3. So we got there from b. Now, what about from b to e? So that is a cost of 6 over here, plus 3, which is 9. So let's compare that against the current cost to get to e. 9 is greater than 5. So this is something that our initial example lacked, right? 9 is greater than 5, so we do nothing. We don't update this. We don't want to go from b to e. That'd be more expensive than going with the cost of 5, right? So we're finished with b. The only undiscovered edge is d. So we've done a, g, b, right? And we can even mark these guys if you wanted to, like that, right? If you had a graph, rather than writing to do done, you could just like mark them with a dot or something, but that's not really going to show up. Okay, so now let's look for the rest of these. We've got c, d, e, and f. C has a cost of 5, d has a cost of infinity, e has a cost of 5, f has a cost of 6. What do you do in case of like a tie, right? C and E. I don't know. Make it up. I'm going to go alphabetically. So, right? I mean, and that's really what it comes down to. You have to use your best judgment when it comes down to a tie. So I'm going to break that tie alphabetically. So we're going to go and say C is done. Now to get from C, so now we know the cheapest way to get to C is by going through B. How do you get to B? By going through G, right? How do you get from C? You go to B. How do you get to B? You go to G. How do you go to G? You go through A, right? The predecessor, the entire point of that is it tells you the cheapest path, right? Allows you to trace the cheapest path as well. Okay, so now we've got to C. C has no outgoing edges, so we're kind of done with that one. So let's go ahead. D, infinity, E5, F6, right? This is the cheapest option. So to get to E, right, the cheapest way to get to E was by going through G. So for a cost of 5. Now let's look at all the outgoing edges from that. To get to there, we've got F, which has a cost of, so we can get, so E to get to F has a cost of 7, right? 5 to get to E, plus the 2 to get to F. And that's 7. Now that's greater than F, sorry, that's greater than the value we currently have for F, so we let it be. So we don't change anything. And so now we're done with E. So now we've got infinity and we've got F. Infinity and 6 for F, right? 6 is less than infinity. All right, so now we've got, so now we look at this, we have an edge 6 plus 1. 6 plus 1, that is cheaper than infinity. So we write down 7 to get to D. 7 to get to D. We get there from F. Right? Okay? And now, finally, let's go ahead. So now we're done with F. Let's go ahead and look at D once more and write 7 plus 1, 8. That's not going to add any more information, right? It's no cheaper to get to, it's a more expensive route to get to C, so we don't take it. So in the end, what Dijkstra's algorithm gives us is this nice path, right? How do we get, and what it kind of does is that it basically shows, it shows us what we might say is a subset of the graph of the cheapest path from A to from A to all the other nodes, right? And I'll show you that it's like a subset by kind of just erasing everything here. Well, not everything, right? So this wasn't the cheap way to go, right? I'm only going to leave the cheapest nodes, or the cheapest ways. To get to B, we wanted to go through G. go to G, we wanted to get A. What about going to E? Well, for E, we wanted to go through G, so we're going to erase the one from over here. Right, you don't have to do this on like any exam. I'm just doing this for illustrative purposes. Okay, what about getting to D? To D, get a D, you went through F. Right, so, and to get through C, you went through B, so we're going to remove this one over here. Right? And then finally, to get to F, we went through B, so we're going to erase this over here. Right, and this is the map you want to use, essentially, the graph you want to use, if you just really care about what's cheapest. Okay? Right, so that's Dijkstra's algorithm. It can be done on any graph with weights. Except that's a total lie. It can't be done on graphs with all weights. It does fail under certain special conditions, which we got to see.